Yeah, next topic in this chapter is metal ion indicators. You already learned the indicators in acid base chemistry, okay? And also the same concept is applied to EDTA titrations. And also you'll see after the midterm exam when you learn the redox chemistry, yes, oxidation and reduction, right? The electrochemistry. Also, you will learn that there is the redox indicators. Okay? The concept is the same. In, there are many metal ion indicators. The principle is that when these indicators make a complex with the metal ions, the color changes. Okay, before complexation, the color is different after the metal ion complexation. Okay, and also idea is that now the EDTA, when EDTA solution is added, and then EDTA now takes all the metal ions from the metal indicator complexes. Okay, yeah, that is the principle. Okay? Yeah. And so here the metal ion indicator color change when they bind to metal ion, bind lesser, yeah, lesser strongly than EDTA does. Yeah? This is important. All right. And this is one of the method for detecting the end point. But there are other methods to detect endpoints. Okay, one is here the metal ion indicator. This is where widely practiced. Okay, in the real application, and also the other one is mercury electrode. Yeah? Using the mercury electrode, yeah? You can directly monitor the total whole process of uh, the titration, and also you can use the, ion selective electrode. For example, when you determine the zinc ion, okay, and then you can use zinc ion selective electrode. Okay, and then you learn the principle of ion selective electrodes, yeah, in the electrochemistry chapters. And classic pH electrode is also applied, right? Because as titration, uh, proceed, you know, the pH changes, right? When the solution is not buffered. Okay, let's take an example. The Kalmagite, right? This is one of the representative uh, the metal ion indicators. Okay, here, okay, the IN stand for the indicator, and before EDTA is added, the indicator Kalmagite now makes a complex with magnesium ion. Okay, but when the EDTA is added, the EDTA now takes the magnesium ion from the Kalmagite, yeah, and then equation is like that. So this one, magnesium indicator color is red, but EDTA, very fortunately, EDTA is colorless, and EDTA metal ion complex is also colorless. Okay, but when the indicator is lost the magnesium ion in this case, and then it is free state of indicator, and the color is blue for Kalmagite. Yeah, now the principle of identifying the endpoint with the indicators. Okay, so indicator must give up its metal ion to EDTA. Yeah? This is a usual case, because EDTA metal ion formation constant is much larger than that of indicator metal ion complex. Okay? If a metal does not freely dissociate from indicator, the metal is said to block the indicator. Okay, yeah, all right. Sometimes it happens. Eriochrome black tea is blocked by copper ion, nickel ion, cobalt ion, chromium, and ferric ion, and aluminum ions. Okay, therefore cannot be used for direct titration. Yeah, in this case, if this is the case, direct titration is not employed. But back titration is good. Okay? For example, um, copper ion is complexed with aerochrome black tea, and this one copper ion is not readily released from aerochrome black tea. And in this case, you add excess EDTA, when the excess means more amount that is required to reach the equivalence point. Okay, in the presence of excess EDTA, this copper ion is released rather easily. That is a back titration. Okay, and first, to the copper ion solution, excess EDTA is added, and then add indicator, and then excess amount of EDTA is back titrated with a magnesium ion. Okay, back titration. The principle is that you add more uh, standard more amount of standard solution, and then the unreacted in this case EDTA is back titrated with other ions. Okay, yeah, that's the principle of back titration, and it is applied to any reaction. For example, in the acid base chemistry. Okay, now let's assume you want to know the weak acid amount, the concentration, and then you add intentionally the more amount of base, and then the left unreacted base is titrated with standard acid. Okay? Yeah, here why the indicator changes color because and for Kalmarite, free Kalmarite absorption spectrum is given here, and it has absorption maximum around let me see 600 maybe 20 nanometers, but when it's complexed with the magnesium ion, yeah, the absorption maximum changes to to the shorter wavelengths, right? This is called blue shift, okay? Around to 550. Okay, yeah. So color changes, in other words. Okay? Wow, this in a table 3 lists common metal ion indicators, Kalmarite, but the kind is not many. You see, you saw already that there are many you see the acid-base indicators, but here there are not that many. Kalmarite, aerochrome black tea, the structure is quite complicated, and the murex side, and you see the blue colored these atoms, they are what they are dissociated, right? They are removed when the metal ions are introduced. Okay, then this one, this oxygen to oxygen is the ligand site. Okay, like that. Okay, and for example, Kalmarite, the color changes depending on pH, right? So in this case also, you have to fix the pH, otherwise color changes just because of pH change. Okay? And this is also can be considered as acid. Okay, and then we can you can define the pK values. Okay, pK2 is 8.1 and pK3 is 12.4. Okay, depending on pH, the colors are different. Okay, but when pH is fixed, you have a constant color. Yeah, only color change is due to the metal ion complexation. Likewise, aerochrome black tea is also is a weak acid. Okay, and as you see, these metal ion indicators can be used as acid base indicator. Okay, and murex side. Okay, you just you read the table, and there are another. Okay? Xylene orange. Okay? Oh, the structure is more complex. Wow. So it has PK6, and color changes. Okay, but after the metal ion complexation, the color changes to red and pyrocatacolor violet. Okay, it also undergoes color change depending on the metal ion complexation. Well, this figure tells the graphically and which the pH region those indicators undergo color changes. Okay, and just you read and get an idea. Okay, now let's consider the EDTA titration techniques. There are several techniques you can employ depending on the situation. The first one is directed titration. Yeah, you have your analyzed solution in beaker, and then you add standard EDTA solution. Okay, and then you monitor the metal ion concentration, or using a indicator, you can determine the uh, what the endpoint. Yeah? Okay, the color of a pre-indicator is distinctly different from that of the metal EDTA complex. Okay, metal uh, auxiliary complex agent is less stable than metal EDTA complex. Yeah? And then back titration. Yeah, this is also a technique that is often used. Okay? As I said, a known excess EDTA is added to metal ion. Okay? Excess EDTA is back titrated with the second metal ion. Okay, yeah, you understand? Uh, this is good for if analyte precipitate in the absence of EDTA. So you make first the metal EDTA complexation by adding excess EDTA, and then the leftover EDTA is titrated with the second metal ion, and this is good for also if reacts too slowly with the EDTA. Oh, well, but I don't think this is not the usual case, and this is good for if it blocks indicator. Okay, yeah, these cases you can employ back titration. And here is the important part. Yeah? The second metal ion must not displace analyte from EDTA. What does that mean? Yeah, let's imagine now you are doing EDTA titration by adding excess EDTA. Now that metal ion is now all complexed with EDTA, and then you have um, free EDTA. Yeah, since you already know the added moles of EDTA, right? And then the leftover EDTA is titrated with the second ion, metal ion, right? And this second metal ion and EDTA formation constant must not exceed original metal EDTA complex formation constant. Otherwise, this metal ion, second metal ion, will take, yeah, will take the original, the metal ions from EDTA complex, right? And then you cannot get the answer. Okay, so the second metal ion must not displace analyte from EDTA. Yeah, this is very important. I think this is only one you can uh, be you'll be um, careful. Okay, yeah, this is this one, right? Otherwise, the things are quite straightforward and simple. Yeah, here is an example. Nickel ion can be analyzed by a back titration using standard zinc ions at pH 5.5 with Xylene orange indicator. A solution of 25 ml of nickel ion is titrated with this amount of EDTA. Yeah, this is excess. Adjusting pH to 5.5, the solution turns yellow when a few drops of indicator are added. Titration with 0.02299 molar zinc ion requires 17.61 milliliters to reach the red endpoint. Calculated molarity of this one nickel ion in unknown, right? You understand, yeah? You want to know nickel ion concentration, and then you added 20 ml of this concentration of EDTA, and this the moles, yeah, moles is higher, greater than initial the moles of nickel ion in unknown, in the unknown, right? And then remaining EDTA is titrated with zinc ion. Okay, now you can immediately note that EDTA nickel complex formation constant is higher, greater than EDTA zinc complex of the formation constant here. And note, Kf for nickel ion, is 10 to 18.4, but Kf for zinc EDTA complex is 10 to 16.5. Okay, well, good, very good. And here is the solution. Total moles of EDTA is 1.3208 millimole, and mole zinc here, you know, is 17.61 milliliters multiplied by 0. Zinc concentration, and it gives 0.4049 millimole. Okay, so mole of remaining EDTA is what? Initial mole is this one, and then the moles reacted with zinc ion is the difference. Okay, that is 0.9159 millimole, which is the also mole of nickel ions, because only the reaction the proceed in 1 to 1. Okay, so concentration of a nickel ion is what? This one, this millimole divided by initial volume, right? 25 milliliters. Okay, and we get this number. Yeah, you understand? Yeah, this is quite simple. Okay, now next topic is the displacement titrate, and then I'll let's stop here.